Very good morning, everybody. This is the third day of our FDP, and I'm very happy to welcome Dr. Satish Kumar Panda, sir, from IIT Bhubaneswar. So, like yesterday, we were in a dilemma regarding the extramural funding. So, today, sir is there here to clear all our doubts and encourage us more to put proposals. Now, to give a little brief into himself, he is basically a mechanical engineer. So now when you say that I am not belonging to the CSE department, I belong to electronics, electrical, civil. Here is a man who is from mechanical department and doing research with ophthalmology and working in generative AI and AI field. And for our, what you call, so the thing is, Sir is currently handling 8 funded projects, 3 from DST, 2 from ICMR. Satish Panda sir is an assistant professor in the School of Mechanical Sciences at IIT Bhubaneswar and affiliated to AI and HPC Research Center. Previously, he served as an assistant professor in the Department of Mechanical Engineering at IIT Guwahati. He earned his PhD in Biomedical Engineering from the National University of Singapore, top 5 universities in the world, and subsequently spent 4 years as a scientist at Singapore Eye Research. His research centers on the image processing and the development of AI and deep learning networks for healthcare and computer vision applications. He has 4 years of industrial experience in Tata Hitachi and Bajaj Auto. So I hope that you will take this opportunity as not just a learning but also as a collaborative experience and establish connections beyond this workshop. Thank you very much. We welcome you, sir, on behalf of CTTC. I would now like to request Dr. Ritu Maiti, the coordinator of this FTP, to hand over a flower bouquet to sir as a token of gratitude. We welcome you, sir. It's a pleasure to have you here.
I'm going to talk about some of my research work. I keep my presentation at a very basic level so that for like a general audience. If you are an expert in AI, maybe it won't be that much relevant for you. But I'll try to, if you have any further queries or in-depth queries about any AI technique, I'll be happy to answer. It's site. So my primary field is ophthalmology, any eye-related side work. So we have a couple of collaborations with the different hospitals, different eye hospitals, collaborative, and we get different kind of images, and then we develop different AI networks and analyze those images by a master. Kind of can do different segmentation or segmentation, and then we also develop an app, and we try to deploy those apps as software. So in my lab, we have already developed two softwares which are currently in use. One is in Bhubaneswar, one is for IIT Bhubaneswar. I was for 5 years. So we have still some collaboration going on, and we have developed the software for now that we are looking for. Currently, we are living in a digital world, and we see that like gravity nowadays, it's everywhere. You look anything, anywhere, it's digital. So it's a very nice diagram I found somewhere in the internet. It says digital is like gravity, it's everywhere. And then so now we're at the stage that we cannot avoid any kind of digital conflict or digital. So I have one question, and just one quick question to the audience. Who can recognize this image? It's a kind of MS image, but who can recognize this image? Anyone? So this is the first digital image of the world. So this image was created by this guy. He's a very famous guy called Dr. Bhubaneswar. In 1957, he created this image, the first digital image. But the interesting thing is, the first digital camera was invented in 1975. In 1975. But the first digital image came almost 20 years ago. So it means the first digital camera didn't capture the first digital image. Okay. So this guy, he scanned his 3 months old son's photo and created the 170 plus 170 plus pixel. So in 1957, it all started, the digital image. And within like 70 years now, everything is digital. Okay? So think about we're kind of surrounded by cameras, digital cameras, we have DSLR cameras, we have cameras on drone, on car, underwater vehicles, everywhere. Okay. So we're capturing so many images nowadays. Like if you think about now, phone also now we have 4 to 5 cameras, right? Everywhere capturing like almost like 50, 60 images. Each of us is 100 gigabytes images in our mobile phone. So there's so many images. We have cloud computing, we have hard drive, we have data storage, we have so many facilities to keep our images. But now the question is what to do. Okay. If you think about your mobile phone, we have so many rubbish images, so many unnecessary images in our mobile phone, right? Like in WhatsApp, we get so many images which we really do not want, but we don't have time to go and delete those images, right? Like so much is consumed by this image. Then what to do with it, right? So we need some kind of system that can automatically see those images, it will identify those images as will be necessary or not necessary, and then simply it will remove. So we need some kind of system that will automatically look at this image and it can say, oh, it's a useful image or it may not be useful and so on. Right? So that's why we have computer vision. Computer vision is a field of AI that basically enables its computers to think, or to analyze its images, and it can understand its images, what is there. It can understand its content, you can understand what is there in that image, it can give you something, some prediction or some information about the image, some useful information, right? So if we think about computer vision, recently we have done a lot of development in computer vision, like in vehicles, where we have the cameras, we have the AI networks that can use real-time image processing, identify cars, pedestrians, or things like that. Similarly, with this computer vision system in our robots, autonomous robots, they can look at the object, they can identify the object, they can do the kind of task on its own. Right? So if you think about AI, it all started around 50s and 70s when people started building neural networks. Because they used to call it a thinking machine because neural network, the neural term coined, I think, 10, 20 years after that one. So they started this neural network design in 1950s. Then in 1980s to 2000, late 2000, early 2000, they started with machine learning, which became very, very popular. Machine learning techniques, different algorithms came, different approaches came for machine learning. Then suddenly in 2011, something big happened and this deep learning came into picture. So the concept of deep learning is kind of similar to machine learning, but those concepts were already developed in 80s, 90s, but they never got this much attention because during those days we didn't have GPU servers, we don't have big data. What happened in 1911, 2011, NVIDIA came up with its GPU card. Then Stanford and MIT, they came with big data sets, like endless data sets, and image data sets came. And because of that, it is possible now to train a very big model with a big data set, because of the GPU. And it's deep learning started during that time. And after 2020, suddenly, this generative AI started. And we are like, almost everyone is kind of now using GAN or generative AI. They start with the consistence that can write essay for you, that can do a generation, that can write a seed, that can write a song for you, anything it can do, right? So now we have this kind of GAN network that can do almost everything. So to go back to this neural network, it's basically inspired from the neurons of our brain. If you think about the neurons have some kind of accents and dendrites, they connect with each other. It is a very deep network. And if you look at this small light sparking, these are known as, if you go to biology, these things are known as action potential. They are simple voltage signals that pass through these neurons. Actually, you can put an electrode inside your neuron, inside your neuron, and you can measure those signals. So you get a voltage signal. It's a very nice and well-structured voltage signal that passes through these networks, and that's how your brain kind of process the data. I'll go to this one later again. But the neural network is somehow inspired from this kind of architecture. The same thing, they create some kind of nodes are connected with each other, and whatever the information is coming to the network is passed through this node. And during this process, they do some kind of mathematical processing on the numbers, and they finally say some kind of prediction about the step. Suppose they have an image of a dog that in that image will pass through the network, and finally they will show the dog, for example. So how the network does work? So what for us, what is an image is basically a set of numbers for a computer, right? So if you look at an image, keep on zoom in and in, then at a certain point you see something like this. The image is kind of the function small blocks. The blocks are on the pixels, and each pixel has a particular value. So what is a nice image for us? It's basically a set of numbers for an. Then when you pass these numbers to this network, so each number will be multiplied, it will be kind of added with something, and some kind of mathematical transformation will be happening on this number, and finally you will finally get it. So this is how the network proceeds, this. And it gets some output from the network. Then now we're at a certain stage that we do not need to really develop these networks anymore. There are big libraries available, they have already implemented, well-trained model available. Within like 2 or 3 lines of code, you can do any kind of image processing. Suppose they have images of different animals, and you want to identify that animal. Then you can do, you can simply call a model. Then you can simply give your location to the image and directly model the brain, what kind of animal it is. The network is taking the red fog, people is taking water, and so on. And this is the number. The next one is basically the confidence or the network is 99% confidence. So these are like very easy nowadays. We really don't need the programming, the knowledge of programming to do this kind of things. Simply you just upload the image, the network is well trained, already there. So not only this kind of classification, the network also can do the varieties or the breeds of the animal. Suppose say you give a image, the network will say with 99% confidence it's a dog. But again, you can classify the variety of the dog. Some words, some kind of bull, I don't know the names, but the networks are so good that it not only identify the animal, but also identify the variety of them and what kind of breed of that animal. Then this is another interesting thing. We have an animal here which is kind of extinct out of preference. And the network never exposed to this particular animal. They never had an image or never saw an image that is similar. But if you see this image, the network still, what you do, we try to find some features and then you say what kind of animal it is. So you see the prediction it says what? Well, that's wrong. But you see the similarity with this one and that animal features. If you know this kind of elevation, somehow the network is kind of find the network finds the features on its own. To compare those features with other animals, then it say, oh, but again, you see the probability is like only 90% here. The network is saying it's a koala. It's not very sure. Saying maybe it's a koala. So the networks are not only identified, they have some idea, they have some intelligence. They can find those features, they can compare those features with other things, and they can predict everything. Networks are so good. So with this, now I'll come to healthcare, just my field where I work. And here there's a lot of applications in healthcare. You can do patient diagnosis, you can do human processing, drug discovery, medical robots, health records monitoring, all the things you can do. Again, I won't go into all these things. I have come to my field of research. I know the field of medical inform. So I'll come to human processing. So in medical field, there are many images. We have X-ray, CT scan, MRI scans, ultrasounds, a lot of images are there. And if you go to any hospital nowadays, it's heavily depend on this. Every time the doctor says they should do an X-ray or a CT scan ultrasound, and then they look into those images, then they say, oh, that. So once you have an image, we usually look for different types of reference. Sometimes we do something called segmentation, we do something called classification or diagnosis. Particularly, these four things are very common in field of medical imaging. Then I will again go a bit deeper. In the field of medical imaging, I am involved in ophthalmology. So ophthalmology is the field of eye, any eye. So I will do a bit more deeper now. So I have a cross-section of eye here. So in your eye, so here you are pupil, then you got your iris, and this region is known as the next side of the eye is known as retina vein or optic nerve. So what happens in this region? You have a lot of cells. So it's called the ganglion cells or retina cells. Whenever some light is coming to this region, falls in this region, and the light is converted into a voltage signal. It's like simple voltage signal. Even you can measure that voltage signal. And then the voltage signal passes through something called an optic nerve to the back side of the brain. And this is known as the visual cortex of the brain. The voltage signal basically goes back to your brain, and the voltage signal is somehow interpreted with its neurons in the brain. And that is how you form, and that is how you see something. Okay. So suppose you have some disease that is affecting your backside of the eye. Then the doctors say kind of recommend a test called optical coherence, ocular coherence tomography. Is a very common method nowadays. So they will scan eyes, and this machine sends a low power infrared light to this region and will capture an image. And once we capture image, we get something like this. This is a 2D image. So this is, you can see this vertical line, right? So there are basically one vertical line is one place, and you have many images stacked together. So this is basically this particular region. If you scan this region, you will finish scanning this region, you get something like this. Post-CT scanning from that posterior part of the line. Then if you take one image from this stack of images, you get something like this. Okay? So here you can see, inside of it, you can see right. So this is the region where you have the issue. This is the retinal layer, you have the retinal layer. And it is inside your eye, this is outside, so gray is here inside. This is the inside of your eye, and this is the issue. And for the retina or the ganglion cells, you see light in the top of the retina. So whenever light comes and falls on this particular layer, the light is converted to a voltage signal, and that signal will pass through this region to your brain. This is how the light. So now, once you have an image, what doctors do, they look at this image, like an X-ray. Suppose you have a fracture, they do an X-ray, then they look at the image, they know it's a fracture. Once you visit, you will see some kind of morphological changes in the structure. The doctor will analyze that structure and then go on. So what we can do here, the task was to, if you have these images, then create a network that can automatically analyze that image and it can tell you whether the disease or not. So for that, we can simply create a network called a classification network. We can create some, I believe the audience has some idea about AI, so I'm directly some AI as well. So we can create a network where we have many convolution layers. You just need to pass this in a full solution layer, and here you have a phrase whether it's healthy or not. This is one way to classify the images. You have image, data network, pass into a training network from those images, and then you have to classify it, whether it's healthy image, right? Then this is very simple, very simple. But the issue with this one is something called a black box. If you pass this image to a network, the network is telling whether it's a healthy or the network, but it never tells you why that is a disease image or why that is a healthy image. And if you do not give a particular reason behind why the image is a disease image, no one is going to accept it. Why? So that is why it's called a black box technique. It never tells you why, what is happening inside. Of course, we know that some mathematical transformation is happening inside the network, but exactly what's happening, what features is created, why it is saying that it is in one house. That is why very difficult to convince doctors to say or the doctors to adopt technology in their clinics. Then what do we do? There's something called a crack test. So whichever you print the black box, then we are coming with a new technique called crack test. You apply this technique on the images, then it will tell you the region which is the most critical or the most important. Then we give the same image, the crash cam will tell you which is the most important region. And this is a reduced image. So compare this image with this one. This is a healthy guy. So you see, it's a very uniform structure and smooth and uniform here. And if you go here and you see the depth here, okay? And you see these diagrams here. So if you have this kind of, this is known as cupping. If you have this kind of cupping, means you have a thing. So clearly the network is identifying those important features, and depending on those features, it's classifying the image as a disease for. So the next one is we can move to this technique saying that see, we say go to clinic, we try to convince the doctor saying that see, this region, why the network is saying disease domains. But still it's not enough for the doctor. They want more. They want exact reasoning. Okay. We said this is the important reason, but that is not still not good enough for them. They want something more. Okay. So that's what we do. We try to then extract some features from the image. Okay. So we create something called a segmented model. So we train a network to identify the layers. This is the issue. There are many sub layers here. There is 9 to 10 sub layers are there in that partition. So we create a segmented model that can automatically identify those layers. Now, after all these layers, the red layer is the most important one because all the retinal cells or the ganglion cells are there. So we created a kind of a network that is an encoder, a decoder, a kind of network. It is an encoder, and the decoder, pass the image to the encoder, you compress it to a small space, and then you decompress it to create something like this. Right? So in this technique, what will happen? The network will learn automatically how to identify the layers and how to segment the layers of this particular system. And at the end, you get that. So this is known as image segmented. The last thing that I did so that you image classifications. Okay. So now my image is segmented. Again, you can do the same thing instead of the raw image or the posted image, you give the segment image to a network, and the network will classify the image for everything. Now, to compare this to a picture, what's the difference? At the beginning, here we supplied the original raw image to the network and classified it. In the second step, we give this segmented image. Okay. So what's the difference there? The advantage here is, if you look at this image, we have a lot of noise here. This region is full of pixels, small noise here, we have some shadows here, all the things are there. Okay. If this image to network, the network gets very confused. It never knows or never realizes what looking is like. That's why your classification accuracy becomes very small or low. But instead of that, if you give a segmented image, something like this, what will happen? All the noise, the shadows, the blurriness, everything is removed. It's a very clean and neat image. If you give this image to the network, we'll get a higher classification. Okay. But I can say this is not enough for the download. We have to go even further. So what we did, next we developed something called auto encoder kind of diagram. Okay. So we say, okay, we have this segmented image, that's fine. We can give it with classification network, we can do classification, that's fine. But that is not accessible with it often. So what we will do is to pass that image with network called auto encoder network. So what this network does is it automatically patches some important images. So you give this image. So for this network, the input and the output both have same. Basically, you're trying to create one image from the same image, and in that process, you are learning some important features about images. And what are those important features? Clearly, we cannot tell what exactly those features are. There are no ways to do that, and it's supposed to be like that. So if you do this one, you'll get some numbers, which are very important numbers, and you can use those numbers again for classification. And then you'll see even a better classification for the other two methods. Why it is happening? Because in this reconstruction process, the network learns something new, something very important about the best, and then it uses those features for classification. Okay. But then again, that is not sufficient for the doctors. They can still it's luck work. They never try to kind of understand the efforts. They try to understand the ideas. They say something more. Then come up with something new like that. What this network does is it will take a segment image, it will pass to a encoder, decoder, and architecture. Then at the same time, it will pass it to a classification network, and the network will try to do kind of image reconstruction and image classification at the same time. Okay. And at the same time, it compresses the image to a small space, and then it will again create the image. So in this process, the network is learning some very important features about this image. And these are the biomarkers of the image. Okay. So this one setting where we pass those segmented images to the network, and then we identify two biomarkers. So two numbers, we have two biomarkers. And we try to plot. So this is my biomarker 1, my biomarker 2. And then we plot it. you will have a very nice structure. Suppose you have, say, 10,000 images, out of the 10,000, suppose you have 5,000 images, or images. If you pass those 10,000 images through the networks, for every image you will get 2 biomarkers. And it is the first biomarker and the second biomarker. They will follow. So each dot in this figure is basically represents one image. I'm trying to represent the complete image using its order. Now, because I have 2 categories of images, one is healthy, one is disease. Certain biomarkers of images, which biomarkers will be kind of similar for healthy and similar for disease. That is what exactly happening here. So only healthy biomarker for the healthy number, they can have cluster here. Now the disease number, very nice. And then we can show this one to doctors and tell them, see, either the biomarkers, you use this biomarker and you have a very nice classification. And this one kind of give us the best performance for the other categories. Then one show this out to the doctor, then they again ask you, what are those biomarkers? What is this biomarker 1 and what is biomarker 2? Again, the same thing, we do not know what is biomarker 1 and biomarker 2. We know it's a biomarker, but we don't know what is the meaning of the biomarker. Again, they ask, what is the meaning of the biomarker? Okay. So for that, I'm going to do one point here, this is the one image. I will put that point towards the other cluster. This is my healthy cluster. One point with that 1 unit. But pull it to the other side, that will gradually move from a healthy to a disease. It means I'm trying to induce a disease in an image. Okay. And during that process, you can reconstruct the image and you can see what's happening. That is what exactly happening here. I take 1 point here, and possibly can pull that point in this particular cluster. And that's what it is. And then you see corresponding tenants. Okay. So see, at the beginning, here I have a very kind of this region, gradually that is becoming thinner and thinner with time or thinner thickness. So now to show this out to the doctor, see, this is what exactly is happening when you treat a disease. You have a very mild and thick tissue. And so now we can show this one. Tell the doctor that we have a very nice and thick piece of tissue here when you're healthy. And when you're moving toward the disease state, the tissue is getting thinner and thinner. And exactly this is the biomarker in clinic. To go to any eye doctor, they know this, but the tissue healing is one of the best biomarkers for digital. And this particular network identifies this biomarker on its spot. We never told the network, oh, go and see the tissue structure, track the tissue structure, nothing. Somehow the network on its own, we got the idea that tissue is very important as the disease classification, we had find this biomarker on its own. And now, if you give this biomarker, the first thing you have a very high accuracy, classification accuracy. And the second thing is explainability. Now you can exactly explain to the doctor if the image is healthy, why it is healthy, with the image is why. And this will help us to kind of gain the trust of the clinician or the doctor so that they can give it predictive. Okay. So I think most of you have seen this kind of network now that are very popular. Apps are available. Suppose say you upload one image, it will tell you how you look when you do folder. So the preload will see at the beginning you have a small clear style and how the face will transform when you get folder and folder, right? Same kind of technology we have applied here. But say at the beginning you have a very healthy tissue, and once you kind of develop a disease, how the tissue will change with time, and we can see that. And it is somehow automatically discovered by the network. We never told the network that, oh, go and see this one, see this feature, and track this feature, nothing. We just give all the images, all the 10,000, 20,000 images to the network, and it on its own, it finds all the things. Right? So this is the one of the results slide, we had around say 7,500 patients. Some of the patients from Singapore, some of them from India, are in the here. And with this kind of classification, we achieved 94% classification accuracy with a sensitivity of 9% and specificity of 96%. And this one is kind of more accurate as compared to a kind of a general clinician. If you go to expert clinicians, yeah, they have different level of expertise. But if you compare this network with a general practitioner or a general doctor, it's more accurate as compared. Because it has like many layers of many networks simultaneously working on the remitters to find the features, different biomarkers, and depending on those things, the trends. So this is all about this particular image thing. Now I will come to a different project. Here, yes, recently biomarker. Other classified markers. It is a augmentation. I think this is when augmentation and do the have the limited number of images. Generally, we make to make the better classification videos for same the the type of not exactly the augmentation process. In augmentation, we have image, we do some kind of modification of process and rotation, flipping or something. Here it is basically segmentation. So we say, I think you are asking about that right? So here the concept is because if you give the original image, it has a lot of noise, shadow, all this things. And the network will get very confused because by not telling the network, go and check the image or something, but simply giving the image to the network. By letting the network to find on its own what is there. Suppose you have a lot of noise in the image, then you'll get confused whether to look at the noise, whether to look at the shadows or this. It doesn't know what to do. Is it related to testing image or what? So like two steps for it. First, you do a segmentation. So you remove all these things, the noise, shadows, and you have a very nice control. Then our second model that is using this segmented images. So what is the best thing is in segmented images you have only the tissue structure and the spatial position of the tissue. So it is very easy for the network now to kind of just look at and focus on the tissue structure, look at the morphology of the tissue, and then that is why to do this kind of thing, it gives usually the higher accuracy compared to the normal. But in image analysis, purposefully people put some sort of augmentation. Yes, also we move augmentation here as well. Okay, when you give this image to our network, we also do augmentation. Like we simply take this image, do some translation, some rotation. Sometimes we kind of flip the image vertically or horizontally so that we can create more and more images. Those augmentations we also do here and with the raw images. But the good thing about this approach is you have now two steps for this. One network is dedicatedly kind of trained to identify the artifacts in the image. The second network is kind of trying to classify or kind of focus on the structure, and that is why you have higher accuracy as compared to one step. Another thing in the moving one cluster, I mean 160 from one clustering algorithm. Yes, it's a clustering algorithm. So there you are saying the reading of the so basically, so here if you look at one dot, it basically represents one image, and one dot is basically two numbers. Okay, so it has a x coordinate and y coordinate. If you look at this now dot here, it is x coordinate and y coordinate. So what we do, we just pick that number and change the x coordinate y coordinate value. And then we have a network. Okay, if you look at the network, in the network we have three distinct. One is encoder, basically compressing this big image into a small metal space. Then we have a clustering algorithm. We also have a decoder. So if you have those two numbers, suppose the two numbers, let's say 1.1 and 1.2. Okay. So from those two numbers, I can reconstruct the whole image, using those two numbers. Now, if I change say 1.1 to say 1.2, Then with that number again, I can go back in this way. I can reconfigure. Best thing is now the complete image is just represented with two numbers. And from those two numbers, you can again create a new image. So now you have the flexibility. Change one number at a time, and you can see the corresponding changes. So these kind of techniques are also now used in any this kind of mobile apps. Suppose you have a video conference app. So you are capturing one image or capturing a video here. Then the video is sent to internet to other phone. Typically, these videos are very memory intensive. They have a lot of memory. And you need a very high speed internet so that the video can be sent to an internet link. In that transmission process, you need a very high power internet. But if you think about current generation, this video quality, even though your internet connection is very low, still you get a very good quality of it. And how they do it. It's totally based on the cell phone. You have an image, then you have a small network that will compress that image into number. So suppose you have a very big image, 1,000% cost 1,000%. So you have the 1,000 square numbers. This network will compress that big image into a very small set of numbers, maybe 5 or 6 numbers. One number is say like 1 KB or 5 KB. It means 5 numbers, say 25 KB. So instead of sending this big 5 MB, 10 MB video or image network, you just need to send those numbers because it's 10 or 20 KB. And those images will be kind of passed in the network. It will go to the other mobile phone. There it will be deconstructed. Okay. In that manner, you need a very less memory or less broadband power, and you can get a very high condition. Okay. Sorry for the coffee. I have it. So this kind of techniques are almost in our video call apps. We very frequently now use this kind of thing. And this is also used in cybersecurity space as well. Suppose you want to share some sensitive information to other party. You don't want to share it directly to them because someone else can read it. So what they do, suppose you have a lot of information, using a model, they compress that information to a small number. And in this number, no one will know what is that number. Pass it, you can give to someone, no one will know what is numbers. Only on the client side, they have this model, and this number will go to this model and create it. Then only they will know this is. Okay. So this kind of networks are very useful also in cybersecurity. Pass it through a network in your user side. Then clients like any customer. So that they go to a suppose some hacker is there, you cannot read or anything you cannot do. So that things get. Okay. So I will move to my next project here. Then here we have a other kind of problem section. Here, what the doctors asked us to, they said, okay, we have this body or the 2D image, and they want to identify the blood vessel structures inside. So we have a very big image, and then inside those images, we have very minute blood vessels, and they want to track the blood vessels. So again, we created different kind of networks that can analyze these images, and if you see this vertical lines here, whenever you see a vertical line at the top, there is blood vessel. So we created some networks that can automatically find those small blood vessel structures, and it can create the complete 2D blood vessel network. And then you can use those blood vessels for variety of purposes. Blood vessels are like in any disease, they change their structure, the biometric in nature to identify a person. You can use those blood vessels to identify a person. Person is RGB conversion from the year to year, like from year to year, right? So, no, first we have a segmented network here that will analyze these images, it will find the blood vessels, slice by slice, then it will kind of create a 2D structure of the blood. Is there any tool available for that? No, you can train it to a network. So you need to create a network, you need to give those volumes to that network. You have to be gradually done all this. The blood vessel tissue. It will try to differentiate between the blood vessel and tissue. And then finally it will realize, oh, this is my blood vessel. Suppose I have a blood vessel here. It will realize, oh, there's a blood vessel here, but it's a tissue here. So it will basically kind of differentiate between your blood vessels that gets used, then it will reconstruct the complete blood vessel structure. And after that, we use this blood vessel structure to identify a disease called glaucoma. And we just give this 3D structure to a external 3D network, and then it will automatically classify the blood vessel structure as a health organ. Because the blood vessels are very important. If you have like high diabetes or high blood pressure, blood vessels that they rupture, so they die. So if you have disease, then it's also very important to practice blood vessel structure, particular vessels you have in your practice. So this is another work that we did. But this has again many applications like your we have this retina scanner, we have iris scanner, and also if you look at the white part of the blood vessels here, right? Those are of the biometric image. You take a photo, that's from fingerprint. These are your biometric images. So these things are also very important in other space like cybersecurity, like monitoring human behavior. For those things, they're very important. Okay, so this is one more project that currently we are doing. Now from the back side, I'm kind of focusing on the front side of your eye. So here in the front side, this is your cornea, there is a pupil here, and the iris. And if you do the same kind of image, you get a figure like this. So here, this is your the cornea, the iris is here, the center of the pupil, and the lens. So there is a different category of digits that affects the front side of your eye. So far, I was focused on the back side, now I focus on the front side. So in this, if you have those digits, they will scan the front side of your eye, and it will come up with an image like this. And then we can analyze this image to find the digits. So we have created a small software in the lab. This is currently used in Singapore Eye Hospital. So you can simply upload one image to the software. Then at the back end, we have a deep learning model that can automatically segment this structure, it will identify the cornea, or iris, and the temple, everything. And then it can do automatic measurements. So simply it will tell you what is the thickness of the cornea, what is the length, the thickness of the iris, what is the shape of your lens, and so on. Automatically it will find all these parameters. And after that, it has other features like iris tracking. Suppose say you are looking at an image or looking at a camera, and suddenly say suppose the change in light, then your iris is kind of respond to that light, and it will constrict. So we have some features to track those deformation pattern of the eye. So this deformation patterns are very important because again, in different diseases, you have a different pattern of your eye. You may have experienced that when a person is in coma, doctor will flash a light from the eye. If the eye is moving, means the person is responding, and the person's brain is working. So in that case, it's very important to track the deformation pattern, how your eye for the figures responding to a sort of light. So we have some algorithms, some networks that can automatically detect or automatically segment the iris. And after that, there is algorithm that can automatically track the motion of the iris. So sometimes, when the patient is in coma, it's totally non-responsive. You cannot do anything, you cannot respond. Then you can do a simple light testing, you put a light scanning, and you can see how fast or how slow the iris responds. Then from that, we can get how time. Then this is another project going on. Here we are kind of more focused on the topmost part of the cornea here. If you take a microscope image of this region, you get something like this. And these are the cells. You can see this is a microscopic image, and these are the cells. And these are known as endothelial cells. These are transparent in nature because at the top of your eye, you have transparent cells. So the light will pass through the cells. So if you have a certain category of disease, what happens? The cells basically they die, and the transparency is basically lost. So what we need to do here, we need to identify how many cells are there in this single patch, and what are the shape of the cells, and how transparent they are. Okay. So we have again another kind of segmentation network we have trained that can automatically identify all the cells present in this image and it will create an image of it. So here it is. All these cells are basically automatically classified. And after that, we have one more algorithm that will go and count how many cells are here, what are the corresponding shape of the cell. And we also kind of interested the shape of the cell, whether it's a hexagonal in nature, whether it's triangle or rectangular in nature, because we are having cells are usually hexagonal in nature. So if you look at kind of this one, this cell, this is kind of hexagonal in nature. It's a very nice and good cell. But here you see this cell, the hexagonality is kind of lost. You see this one, it's kind of lost. So at the corner, the cells are kind of tiny. So the doctors, they want how many cells you have in this particular patch. What is the shape of the cells and what is the density of the cell? So we have, I got this out. So here in this patch, you see, we have some cells here. These cells are basically very big because they are kind of merged together. They're not healthy anymore. This is the black region where the cells are already dead. That's what your black region. That region is not transparent, so light cannot pass through that region. So basically, if you have something in this region, you cannot see that. You will see you lost a region and a region of that. So we have a network that will segment all these cells. That will then it will do a cell counting. How many cells are there? What is the density of the cells? Area of the cell, the standard deviation, hexagonal count, and everything. Okay. And you can give like big images like this one. So you see, this is one more image. This is the corresponding manual segmentation. If you give this image to a doctor, he will mark these cells manually. And this is the network what the network predicts. Very similar to what doctors will find that. So within like a millisecond now, we can just upload an image. You can get a complete report how many cells you have, what kind of cells, what the cells, so on. And then you can so this is all about ophthalmology. We have also like a couple of more projects going on ophthalmology where we are trying to track the eye mode, how people is responding to light, how people are moving, suppose you are reading something on the screen, how people is moving, how they're responding. So we are doing some projects on that one as well. Currently, we started a new project with AIMS now, where we are tracking the eye for mental health checkup. Suppose say it has been under depression or any kind of mental disease like schizophrenia, the eye responds very quick to questions. So we have started a project where we are tracking the back side of the eye, how the systems changing, and then from that one we're trying to understand whether we have any depression, whether we have any very quick for the lie detection. Like that. Light detection, people reflex tells you about your behavior. Okay. So usually when you are kind of lying, your people respond a bit differently. So the light detector they usually track the people person. Okay. So I cannot be. No, retina cannot be tracked, but your people, how your eyes and people are responding, that is somehow related to your behavior. Okay. Yes, okay. Because the best thing about eye is directly connected to your brain. So eye and brain is basically the same structure. The which one is the more connected? Eye is more connected because it's direct extension of your brain. Ears are like connected, but it's not that much direct. Okay. So anything happening inside your brain that directly affects your eye. So like you don't think the person is lying or I respond, people respond. So anything anything that's first affect your eyes, it will be detected first. If you're very high, like diabetes, high sugar level, your vision becomes blurred after some time. So like sugar level, say 400, 450, usually because people cannot see properly, they have a blurry vision because all this vision first affect your retina. So that is that. So if you track your eye, you can do a lot of things. Biometric, biomarkers for a lot of diseases. That is why we're more interested in that. So now coming to a different project, which we started with in hematology field. So what we're doing here is we have some images, some blood smear images. remember, we had blood test in the ticket, take a big blood and they put on a glass slide and they take image of the numbers, right? Then, if you take image, you'll get something like this. So we have RBCs, red blood cells, you have white blood cells, then you have platelets. And suppose you have anemia or some disease, usually doctors go and check how many blood, what are the WBC counts you have, right? They usually do the WBC and RBC report, and they say, oh, we have less WBCs, so you must take, if you say less RBC, then you say iron pills or iron tablets, right? So currently, this is a kind of a manual task. If you give this image to a kind of a technician, you look at the microscope and he will try to figure out how many RBCs are there. Okay. Of course, there are some automated machines available that can do automated cell counting, but very expensive. One method costs you $1. If you go to a very small clinic, they have small microscopes where they put this slide, they look at this image, and they try to figure out how many WBCs you have, what they say to the WBC because. So this is a big WBC here. This is the nucleus of the WBC. And if you look at the shape of the nucleus, you can figure out what kind of disease you have. So if you give this image to a network, the network will automatically identify those features and it can tell you whether you have anemia or any kind of blood related. So again, we have a couple of networks here that can do automated cell counting, automated RBC WBC identification, and then it will tell you what kind of disease you have. Okay. This is one more image we have. This is a leukemia one. Here you see this one WBC here, and it's safe to the nucleus. It's very different. So we have some networks now that can automatically identify the WBC. The nucleus of the WBC, you can analyze this safe, and then it can tell you whether you have anemia or leukemia. The same thing, we have a couple of more networks. So you see, we have like multiple WBCs here 1, 2, 3, 4, 5. Okay. And the nucleus of each WBC is different. And depending on the shape of the nucleus, we have different categories of WBC. Okay. So like basophil, eosinophil, so many categories of them. So we have now some networks that can analyze not only that can detect the WBC, but also it can detect what kind of nucleus it has, and then it will tell you what kind of WBC. So again, the shape of the cells there. Then after that, this is one commercially available app. So you can simply upload a image here, click on the submit button, and it will tell you what kind of WBC you have. This is a commercial app, okay, not from IIT or something, it's already available. So currently we have such apps because we have okay, I don't have because we have also developed a similar app in our lab. You can simply upload a blood smell image to the software. You can identify all the WBCs, RBCs, you can identify the nucleus of the WBC, and it will tell you what kind of WBC that is and what kind of CTs you have. So these are all about hematology. We have many things for again. I'm not going to get into all this in detail. That's all about my presentation. So I mostly work in the field of 80% time I work in the field of ophthalmology, then sometimes I work in hematology field as well. And we have a couple of more projects going on in automatic navigation, there's autonomous navigation, a couple of projects on agriculture side also. Okay. So yes, anything, any doubts, I will be happy to. So, in terms of projects, nowadays, I see a lot of calls, like every alternate week, I see a new call, a proposal for funding. So currently, I believe like there's a big push from the central government as well to for different kind of funding. So I see regular fundings from ESP, from HCMR. So yes, well, really interested in the price and proposals. ICMR has like frequently they have come with new proposals. Currently, I think there are 3 proposals, but maximum 4. Anyone interested in getting those, can apply. Here that the molecular level of represented. So that like you presented can say that the biomarker representation of so biomarkers usually different kinds of biomarkers are there. One is the molecular biomarkers where you look at the gene and genetic structure, then you find out the biomarker. The second kind of biomarker is structural biomarker, like OTT, then you say the red layer at top. The thickness of the layer is usually well accepted as well documented biomarker. So, usually go to any doctor, any ophthalmologist, they will track your thickness of this tissue. Well-known biomarker. So this is a structural biomarker. That's been different from your genetic genomes. But this is again a biomarker, which is well known. And we're trying to find that biomarker. But the issue is that if you look at those images, doctor has 5 to 6 well documented biomarkers, like the thickness of the layer, the curvature of the layer, how the cup, how big is the cup. So all these things are like well known and well documented biomarkers, and people are using for the last 56 years. But now the thing is, if you look at the image, it's a very big and 3D image, and we have only say 5 biomarkers. So you cannot get more biomarkers because we have a limitation. So we doctors really manually inspect those images and then show this may be a biomarker. So it's kind of a limitation because they cannot analyze a lot of. Now with AI, we can give like millions of images networks, they can automatically find a new biomarker. So the one that I showed you is basically this particular model. It's trained with this one. This particular model is trained with 35,000 images from 11 countries. We have countries from Africa, from Europe, USA, Asia, Australia, everywhere. This model is a very big study, it's a $25 million grant in Singapore. So we kind of collaborate with all these 11 different countries. Then we capture 35,000 images. And then we train this network. So proprietary or open? It's the network is not open, but yes, you can send an email to your hospital, they can collaborate. I'm not a part of Singapore hospital anymore, but yes, this network is there. What about the data is not available because it's a part of the grant of Singapore hospital. So they invest in $35 million grant. That grant they capital of the data. That data with Singapore hospital only, we cannot access those data. But also people are being restricted to data because we need data. These are like data hungry models. We need a lot of data. And getting data is very difficult nowadays. Go back like 4 or 5 years ago, still it was very easy. Currently, even our central government has come up with a new Minister of External Affairs. They have come up with a new plan that you cannot share data outside the country. It's a new rule. If you want to share even a single image to your collaborator who is outside India, you need to get permission from some of them. It's like almost important. Okay. So that is record. That is basically record because data privacy and the personal data is very important. 5, 6 ago, it was not there. It was very easy to just give the images, taking it from anywhere. But now the rules are very, very strict. Even getting images from hospital is very difficult now. Sorry? Pseudo data. Pseudo data again, other fields is fine. Taking the information of the place. Yeah. If you are in a field of, like, say, autonomous fabrication, this automatic cars are there. Right? For those fields, pseudo data is fine. You can create a synthetic image, you can train a network on that. Okay. Suppose there is a car, there is a Toyota car in the road, and you are saying it's a Maruti, it's fine. It's not about that synthetic data. I'm talking about data of the website, but we don't require information about the website. Okay, yes. So the anonymous. Yes, that is kind of mandatory now for every project. Even the joint projects with hospitals, still we do that anonymized. We remove all the question data, then we transfer it. That is there. But if that will also you cannot transfer your data outside the country. That is the new norm. Inside the country still it's okay. But again, in your collaborative institute, there should be an ethics committee. Yours there should be an ethics committee. And the ethics committee usually has some external members in there. They need to kind of approve your whole proposal. Then only you are allowed to transfer the data. So like you're transferring data, we are doing some projects with for that, we have an MOU. We have ethics committee. Again, the ethics committee is human ethics committee is different. Institutional ethics committee is different. So there are two different ethics committee. So the committee approves proposal on this side, on IT side, the proposal approved on the Metra side as well. Then there's an MOU after that they start that transfer. So difficult now. When you use operating platform for public data, kind of thing. Then you must be sharing those data with something. No, we don't share the data. That we don't say the data. Only the data settings. Unless you say this is open source data, you upload in net. But that is again like almost impossible nowadays to upload the patient data directly. In medical field is very difficult. In other fields, it's fine. Like we have some projects going on autonomous navigation where we have to simulate the road. That is easily upload, no one cares so far. But for medical data and particularly for this field, because eye is very important organ and it is biometric in nature. The eye can identify a person from the okay. So it's very sensitive data. So almost impossible nowadays to upload this data to any whatever exists that is there. But now for the new rules, it's very, very difficult. If you really want to make new data open, then you will need to get permission from your community. If you the project sponsored by CTTC or ICMR, you will get permission from there. Okay. But one good initiative is from ICMR. Any project that is sponsored nowadays, it asks PIs to feed the data to the central server. ICMR is the central server. So all the projects, whatever data is collected that is there in ICMR, then it is available. So anyone can register an ICMR folder, they can send a formal request and they can access it. So that is the Indian specific method. So there's a very nice initiative from ICMR. They have started this now, I think, from last 4 or 5 years. So any project they are funding, they are the PIs, they are the group. And of course, all the security concern, privacy concern, everything is, they have a panel writer software, but they is a repository, you can get data. Maybe feeling like there is a number of ML models are so the major difference between your CNN or deep learning between ML and deep learning. In ML, the rules are defined. So you give an image, the rules are defined already. You say this is the data, and this is the what's in the data, and then very the data. This is already going to do that. In deep learning, the rules are not like this. You get it driven. Give the images to that automatically analyze the data and it will come up with it. So like for this one, okay. If I want to do a ML model here, what I'll do, I'll say, okay, in this image, I say 10 different biomarkers. I know that is, that's there. I'll extract those biomarkers, then I'll give it a model. So the rule is defined. I know this certain biomarkers there. I will write an algorithm that will get those 10 biomarkers, then it will do it. ML model like that. But in deep learning, you do not need that step. You just need the images to this network. It will automatically analyze all these images. Again and again, 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 look into those images, then it will come with those. So in that sense, you really don't need to formally write down these are 5 or 10 things that you have to find and then you tell the data core, find things, or then you do this. Different simply to find all these things and for, and then it will. But the other thing is we need a very big data set. ML model, you have say 500 images, 200 images, still fine. And deep learning, you need 10,000 images, 20,000 images. Yeah. Even those, how long will it take to train? It depends on the size of the data set. For this one, 35,000 data, it took us around on a this model was trained like 2 years ago when I went to data. So we had a RTX series review card like that, and that model took that card took almost a week trade. Now we have a new generation GPUs. Currently in my lab we have A series. The physical so you depended on the physical system. The physical system. When we since we belong to private and high, we have restricted the and all the things. We always depend on Colab and Colab. Colab also like DQ, but it's not again very limited. That is very takes even 2 3 days. We have to do you have any solution for that? No, I mean, Colab is there, then you have the Kaggle also there that provides some more DP, but still again, it's not that good. Yeah. Or else you can borrow GPUs like even paid, something. Yes, it is so. Like when I was in IIT Guwahati, we had a center called then that center they have very big chicken festivals. And simply you can pay minimum charge, and for education should they give that very minimum. And then they'll give you okay, and so from here you directly give a when you go to that. And I think I think 4,500 rupees for 24 gift card. And you can use that one for a month, or you can do a subscription kind of thing. You can say I need gift card for a week or a month. 5,000 max to kind of rupees to get great. So we are coming in IIT, we are coming with the NVIDIA GPU lab. Maybe another 4 5 months. But we are coming with a very big NVIDIA GPU system. Once that is online again, we'll kind of open that. Very small, mission. And I think nowadays all the super company facilities are there. They give this kind of facilities. You can pay a minimum amount and they can right. Just the documentation part is which I forgot them all this. They need to send them a formal reply. Put them take some time to. The market is done then you can use it. You know, while training the thing, we need to since the emails are we need to for training validation immediately training how the so we have like 3 data sets. One is training, one validation, one testing. So during training, every person will training. Then we will validate the data set will find the accuracy. Then we track the accuracy. Then we get involved. If the accuracy is kind of not stable, then we say once the data is trained, then when you try the network on it, test we call it still 1.1. So for the reduction data set, do we need to choose the best samples or randomly things? So there are 2 approaches here. One is called a K-fold validation, and it's called a Monte Carlo simulation. So in K-fold, you have the data set, you split your data set, first you're doing a 5-fold validation. So split your data set into 5 parts. At the beginning, you take 3 sets in training, then next time you take another 3 in training, and so on. 5-fold validation. In Monte Carlo, you have a very big data set, you randomly shuffle the data set, and split it in 3 parts. You take 1 part, you train validation. So then you train the network, you get that. Then you do one need to be a pocket data set or random. Actually recommended to have a random sampling. So otherwise bias will bias with that. So what we usually do, we have to big data set every time we shuffle it, train the network, do a backlist. Again, we do the shuffling, one more after it. Okay. So we do the shuffling for like 100 times. And then we say this is the mean and correlative. That is the Monte Carlo. This is the best one. But again, it takes very long because 100 coupling and running this like months. So instead of that, you can do it 5-fold analysis. So where basically you have 5 something kind of thing with this kind of quick tool, but not that robust. So like suppose that you are doing this coupling, and by chance you have very good data in your testing set, then you'll get very high accuracy, right? And some other time you have very bad data in your testing set, you'll get a very good. So with one iteration, you can never say the exact what is the exact accuracy of the network. So that's why you could sample it again and again, and then you come up with the mean and another thing. Now here one more thing to the tool thing. Somebody has certified that true ground truth, right? For us, the doctors will be for us. So all these images, we collected these 35,000 images. So we had in the hospital, we had a dedicated team of doctors, 3 doctors, expert level. And what is these are proprietary or open level? Ground is our because it's their work and their unless if you have like a collaboration to them, then definitely they will open those data for you. Otherwise, but we need to have a okay. Like current in this ICMR project, we had collaboration with Ames Nagpur. So we capture images there in their ophthalmology department. Then we have 2 doctors there and a field so at the end we get all the things. We get that. It is not possible for us. Although I have been working this field from 5 years, but still it is not possible for me to get expert papers in the field. So the doctors are there in the institute. And the good thing is ICMR given us fund for the recruitment. So we kind of hired the doctor. Okay, for 3 years, salary there for 6 years and then the overtime. So any proposal nowadays, even ICMR accepted this one, they give you good salary. Suppose they have a senior research scientist, 3 positions, but the salary is around 80,000 per se, so around 1 lakh, little more than that. So you can have a provision to keep that fund for say 1 year or 2 years, and you can hire a technician or very doctor. So that we need to create this circuit. Otherwise, very difficult. And we need to down to provide it. Yeah, I remember quite difficult to get set out. We get outside images, specifically US. Those yeah, the big issues in black transport and many everything is written basically that is open source. But yeah, from Indian side, yeah, to create those services. But the good thing is ICMR is gradually creating, like after say 4-5 years, all the medical data from ICMR will be available in India, not outside for India. It will be available. So painting, I don't know about BBG and DSP, but yes, ICMR very active being on it. And every month they do a review meeting and they ask for the data on the analysis. The data they have central server, after all the that's it. The IIT Bhubaneswar doing any offline coaching to AML classes? Not with target. Not with target. Like offline for courses for AML. Like for students, right? Or for anybody who wish to learn a student. Yes, we have a new center now. In that center, we have some plans. So we have already started recruiting PhD and MS students. Anyone from any field can join and do a PhD apply here. Someone from biology background, someone from computer science background, mechanical background can do a PhD in sector and apply here. So it will give a follow up and he will apply here. He doesn't need to develop his networks, but he can simply fix some networks and apply. Like in this work, okay. Some work we have where we use this already available network. For other work, we will develop our own network extra, the training. But for other work, we can take a network available network training. So that kind of programs are there. We are also planning a program for MS program for doctors. Doctors can join MS program where they will get a degree in data science and particularly. But again, in the pipeline, okay, it takes some time to formulate all the things. What is gate for gate score is required for PhD? No. If you have an MTech degree, no gate required. Okay. Now nowadays, all the gradually are kind of IITs, the University part they are giving the 6 months online course. Online courses are, but Bhubaneswar doesn't have this thing yet. I think Guwahati has. Guwahati has. I used to get classes in this one when I was there, but here we are planning now. Maybe after because of university in the Caltech, they are collecting much more. Yes. So there's a very profitable program also. Okay. So only the certificate from the IIT. Yes. So in Guwahati, when we started the program, in the very first year we had 5,000 registration for this program. So this is a, I think 9 months or 1 year program. Yeah. Application. So these programs are now very popular nowadays. Yes, in Bhubaneswar side, we are yet to start that one. We have all the plans there. Maybe another 6 months already has to start. But currently, we are actively working on the MS for doctors that program. So doctors will come and join the program. They will either do a PhD or MS degree on applied AI on medical data. They will be ready that is for actively considered for that. But if our PhD and MS program is now over, anyone from any field can join. And if you have an MTech degree in engineering field, you do not need GATE. If you do not have it, if you have a BSc or something, then you need to have a GATE. Thank you so much.
Senior manager training is done.
I would like more.
So, participants, how was the session? Good. Okay. Okay. Thank you very much. Thank you, Satish sir, for coming all the way from IIT. And now I would like to request our Senior Manager Training, Dr. K.M. Rajan, to give a token of gratitude to sir. Yeah.
How is the second going on?
Yeah.
I think you had the hands-on right?
Good morning, everyone. So after this first session, now we'll move on for the hands-on session. So yesterday the lab was there. There only we'll have it. So you people need some break or like we'll directly go there. Yeah, while we go there, it's itself a break actually. You have to climb stairs now. Okay, so we'll go to the lab now. Thank you.